Hey guys, welcome to this video 4 of the thermodynamics series. In this video, we're going to take a look at different methods of heat transfer, as well as the zeroth law of thermodynamics. Let's get into it. So as a question sort of as review from the last video, I challenge you to pause the video in a second after you've heard the question and try to answer it. If I have 3 blocks at 3 different temperatures, and I put them all in contact with one another, when will the heat flow stop? Pause and try to answer that. Well, hopefully you remembered that the heat flow will cease once all blocks are at the same temperatures, because we established that heat flows from a higher temperature object or location to a lower temperature object or location. Now in this case, where we have solids in contact with one another, we call this conduction. So conduction happens between 2 solids and usually occurs because the particles that are more excited in the higher temperature object come into contact with the molecules in the lower temperature object and thereby excite them, losing energy from the higher temperature and gaining it in the low temperature. Now if we were to say that block A was in thermal equilibrium with block B, and block B was in thermal equilibrium with block C, then we would have to say that A and C must also therefore be in thermal equilibrium with one another. Now this seems very rudimentary and very simplistic. You may have heard it in a math class or a logic class as the transitive property, and it is the transitive property in those terms. But in thermodynamics, it actually indirectly supplies us with a very important idea. And that is that temperature is something measurable between different systems. It is something that can be measured absolutely between these 3 different systems. In other words, it's not just a relative term, it's actually a description of the particles in contact with one another. Now, I think also indirectly, it helps us establish the idea that heat flows from high temperature to low temperature, and eventually heat flow stops when thermal equilibrium is reached, where the temperatures are all the same. This law became so fundamental that it became known as the zeroth law of thermodynamics. Now, you might be wondering, why is it called the zeroth law? Well, there were already 3 laws of thermodynamics that were established. We're going to unpack several of them in this video series. But the zeroth law was discovered after that fact and seemed so fundamental in connecting the other 3 laws to one another and establishing some of the fundamental ideas that we needed to be able to measure to describe the other 3 laws that they decided, instead of naming it the 4th law, it logically should be named the zeroth law, because its understanding comes before understanding the 1st, 2nd, and 3rd laws of thermodynamics. But enough on that now. We'll get to it later in a different video. If you've ever heard the phrase, hot air rises and cold air sinks, you've actually been hearing about the 2nd method of heat transfer, known as convection. Now, convection occurs in liquids and gases, and it's actually usually the most efficient way to transfer heat. Now, the basic mechanism by which it works is that hot gases or hot liquids move up to areas where you have cooler liquids or gases, and thereby can create a sort of cycle. Now, we're going to take a look at this in a slightly bit more detail. So if we think of the idea of density, mass per unit of volume, when the substance is heated up, let's say down here at the heat source, the volume it increases, the object expands. Now we're going to get into that in a lot more detail later in this series, but let's just take a look at this from a very generic standpoint. As this volume increases in this region over here between the molecules, we see that the density actually falls. And we know that in areas where you have less density, the less dense objects or regions will start to float. And so as the volume increases and the density drops, the warmer air tends to move upwards towards the cooler air. Now, when they come in contact with the cooler air, those molecules knock into the cooler molecules, or the molecules that are moving less excitedly, and thereby excite them. Now, As that happens, they lose the energy that they initially had brought up to the top or to the cooler area, and they will start to fall back down again and then get excited again, and the pattern will continue on and on and on. If you've ever heard of a convection oven, it's an oven that is used often in restaurants and catering. Some homes have them as well. Convection ovens actually more quickly and more efficiently prepare the food, because they're able to have this moving heat flow throughout the oven that creates a very evenly distributed way to cook and prepare the food. This enables it to be cooked the same on both sides and not just on the side where the heating element is placed. The final method of heat transfer that we're going to take a look at is known as radiation. And we're not going to explore it a lot in this series because it usually takes on its own study. Both conduction and convection require matter to transfer heat, but radiation is a method of heat transfer that does not rely upon contact between the heat source and the heated object. For example, we feel heat from the sun even though we're not touching it, and there's no substance really between us and the sun that is uniform enough to transfer that heat. Heat can be transmitted through empty space by what we call thermal radiation. And thermal radiation, sometimes called infrared radiation, is a type of electromagnetic radiation. It's a kind of light, if you will. Radiation is a form of energy transport consisting of electromagnetic waves traveling at the speed of light. No mass is exchanged, and no medium is required. Objects emit radiation from quantum phenomena, and so we will not really focus on them in this series in the thermodynamics course. But definitely look out for radiation because it's one of the most important and most fundamental of all our modern physics ideas. Our last focus is going to be to look at the rate of heat transfer. Now, how quickly heat transfers could be approached from many different standpoints. Now, we already have established that heat flows when there's a difference in temperatures. So it kind of goes without saying that if there's a greater difference in temperature between two locations, there will most likely be a faster heat flow. But let's see what else can affect the rate of heat transfer. Now in the winter, you put on a jacket. Now, not all jackets are created equal. Some jackets, although extremely lightweight, can be extremely insulating and keep you very warm, where other heavy wool jackets might not keep you that warm at all. It has to do with several different things about the layer between the two systems that are trying to reach thermal equilibrium. So very basically speaking, the rate of heat transfer is the amount of heat that passes the barrier or the boundary in a given amount of time. Now we've already established that there's probably a direct proportion between the difference in temperature of each system on either side of the boundary and the amount of heat that will flow between the two. We can also say that the larger the area, the more heat is able to transfer. This makes sense just by sheer geometry. You can come into contact with more molecules if there's more space or more surface area. Now the thickness of the boundary is very important. We know that a very thin t-shirt versus a very thick cotton jacket can be a lot better insulator. In other words, there's an indirect or inverse relationship between the amount of heat and the thickness or the distance of the boundary. Finally, the kind of material that is the boundary between the two systems will be effective in allowing heat to transfer or not. For example, a styrofoam cup is a lot better insulator and prevents the rate of heat flow between your hand and your hot coffee more so than a glass does. But if we take a look at this kind of material, based on its molecular structure, we can call it a thermal conductivity constant. In other words, different materials allow heat to transfer better than others. We talked about this in a little bit of detail in the last video. Now all we worry about here is just looking at this main equation as a way to describe the heat flow the rate of heat flow from one space to another when there's a boundary in between. So that's it. In the next video, we'll take a look at thermal expansion and see how it has many applications in our cities and daily lives.